Good morning, all of you. Today I am going to make an audio recording for visually impaired student of organic chemistry book. Name of the chapter is Ultraviolet Absorption Spectroscopy. Introduction. One of the most important field of activities of an organic chemist is the determination of structural formula of various substances. In the earlier days, the structure elucidation was mainly based upon the study of classical physical properties. It means melting point, boiling point, refractive index, etc., and chemical reaction of the compound. The procedure involved was rather laborious and time consuming. However, in the last 50 years or so, many remarkable physical methods have been developed to serve as powerful tool for structure analysis. Of these, the most useful and commonly employed method are the spectroscopic method, which are based upon the interaction of electromagnetic radiation with the substance under experiment. These methods may further involve the study of ultraviolet, infrared, nuclear magnetic resonance, and mass spectra. Mass spectroscopy is employed to determine the molecular mass and molecular formula of the substance, while UV and IR are used to determine the nature of the functional group. Finally, the NMR spectroscopy is used to know the complete structure, including the stereochemistry of the substance. The major advantage of employing these spectroscopic method for structure determination and identification of substance are as follows. First, they need very little time and the information obtained is often a permanent record in the form of a chart. Second, the substance is required in very small quantities. The methods are extremely sensitive and highly reliable in establishing the structure of compound and analysis of mixture of closely related compound. They can be used for the detection and identification of even very short-lived reaction intermediates. During the spectroscopic studies, except mass spectroscopy, the compound is not generally affected chemically and can therefore be recovered unchanged. Continuous analysis is often possible, facilitating the study of reaction rate, etc. In this chapter, we shall deal with the basic aspect of ultraviolet spectroscopy. The electromagnetic spectrum and spectroscopic studies. First is electromagnetic radiation. Many spectroscopic techniques are based upon the interaction of compound with the light or some other form of electromagnetic radiation. It is well known that light and other electromagnetic radiation are different forms of energy which have a dual character. They have the properties of both a wave and particle. They are called electromagnetic radiation because they consist of oscillating electric and magnetic field which are perpendicular to each other and perpendicular to the direction of motion of the radiation. Some important characteristics of these radiations are: first, the energy of these radiation is inversely proportional to the wavelength or directly proportional to their frequency. These radiation do not require any physical medium and can be determined through empty space. For example, light reaches us from the sun through empty space. All type of electromagnetic radiation travel through space with the same velocity, which is nearly 3 into 10 to power 8 meter per second inverse. Electromagnetic radiation can be described in terms of their characteristics such as wavelength and frequency. First, wavelength is the distance between two adjacent creases or trough in the particular wave. It is denoted by the symbol lambda. The wavelength is usually expressed in meter, micrometer, nanometer, or angstrom. 1 micrometer is equals to 10 to power minus 6 meter, 1 nanometer is equals to 10 to power minus 9 meter, and 1 angstrom is 10 to power minus 10 meter. An old term for micrometer is micron mu, and an older term for nanometer is millimicron mu. Frequency. It is the number of waves which pass across a point in 1 second. It is denoted by the symbol mu. The frequency is generally expressed in cycle per second or simply second inverse or hertz. The frequency and wavelength are related to each other as mu is equals to c by lambda, where c is the constant velocity of light. Third is wave number. It is the reciprocal of wavelength and represents the number of waves per centimeter. It is denoted by the symbol V bar. Wave number is generally expressed in centimeter inverse reciprocal centimeter. Wave number is related to wavelength and frequency as mu bar is equals to 1 by lambda or mu by c, where c is the velocity of the radiation in centimeter. It means 3 into 10 to power 10 centimeter second inverse. In SI unit, the unit of wave number is meter inverse. Fourth is energy of electromagnetic radiation. Electromagnetic radiation are associated with this discrete energy units called quanta or photons. The energy of the photon is directly proportional to its frequency or inversely proportional to its wavelength, as shown by the following equation: E is equals to h mu is equals to hc by lambda, where h is Planck's constant and its value is 6.625 into 10 to power minus 34 joules second. Electromagnetic spectrum, visible light which can be detected by human eye, constitute only a very small part of the electromagnetic radiation. The full range of these radiation is indeed very large and their wavelength vary from a very small fraction of a meter to many kilometers. The arrangement of entire range of electromagnetic radiation in increasing order of their wavelength or decreasing order of their frequencies is known as electromagnetic spectrum. The complete electromagnetic spectrum, along with common names used in the identity different range of wavelength, is shown in figure 4.1. Cosmic rays and gamma rays, X-rays, vacuum, ultraviolet, infrared, far infrared, microwaves, and radio waves. Of the complete electromagnetic spectrum, spectroscopy techniques are concerned primarily with radio frequency radiation, infrared radiation, and ultraviolet visible radiation. Principle of absorption spectroscopy. It is interesting to note that particularly all the important spectroscopic methods used for structural analysis belong to the field of absorption spectroscopy, which study the absorption of electromagnetic in relationship to molecular structure. When a beam of electromagnetic radiation is passed through a substance, the radiation may be either absorbed or transmitted depending upon the wavelength of radiation and molecular structure of substance. Absorption of radiation would naturally bring about a change in the increase in the energy of the molecule, the energy gained being directly proportional to the frequency or inversely proportional to the wavelength of radiation. The increase in energy of the molecule may lead to electronic excitation, whereby electrons are raised to higher energy levels. Alternatively, it may be bring about an increase only in the vibrational or rotational energy level of the molecule. Electronic excitation can be caused by only high energy radiation such as ultraviolet and visible radiation. On the other hand, vibrational and rotational energy level can be raised even by relatively low energy infrared radiation. A very important condition for a molecule to absorb electromagnetic radiation is that the energy of a photon of the radiation must be equal to the energy difference between two vibrational or rotational or electronic energy state of the molecule. In other words, the particular wavelength of the radiation that a given molecule can absorb is determined by change in vibrational or rotational or electronic states that permitted to a molecule of that structure. The observation absorption of radiation is, in other words, the particular wavelength of radiation that is a given molecule can absorb is determined by change in vibrational or rotational or electronic states that are permitted to a molecule of that structure. The absorption of radiation is observed instrumentally by passage of radiation through a sample of substance and automatic analysis of intensity of transmitted radiation. A record of the amount of radiation absorbed or transmitted by a given sample as the function of wavelength of radiation is called absorption spectrum. One might accept an absorption spectrum to consist of a series of lines, but actually the spectrum is made of absorption band with peaks of maximum intensity. The instrument used for recording a spectrum is known as spectrophotometer or spectrometer. Having discussed the principle of spectroscopy, we proceed further to discuss ultraviolet spectroscopy in some detail. Ultraviolet spectroscopy. UV spectroscopy involves the measurement of absorption of light in the visible and ultraviolet region. Visible region 400 to 800 nanometer, UV region 200 to 400 nanometer by the substance under investigation. Since the absorption of light involves the transmission from one electronic energy level to another within a molecule, UV spectroscopy is also known as electronic spectroscopy. It will be quite appropriate at this stage to study the laws which governs the absorption of light. The absorption law. There are two laws which express respectively the relationship between absorption of light by a substance and its molar concentration and length of the path through which the light passes. These are Bayer's law. First is Bayer's law. According to this law, when a beam of monochromatic light is passed through a substance dispersed in a non-absorbing solvent, the absorption of light is directly proportional to the molar concentration of the absorbing substance. Second is Lambert law. This law states that when a beam of monochromatic light is passed through a substance, The absorption of light is directly proportional to the path length of the sample of the substance. Beer-Lambert's law. The two laws stated above can be combined to get a general absorption term known as Baird-Lambert law. It may be stated that absorption of light by a substance at a particular wavelength is proportional to the number of molecules of the substance in the path length. Mathematically, log I naught by I is directly proportional to C Baird's law, and logarithm I naught by I is directly proportional to L Lambert law. Baird-Lambert law may be expressed as logarithm I naught by I directly proportional to CL. Logarithm I naught by I is equals to epsilon CL, where I naught is the intensity of incident light, I is the intensity of transmitted light, C is the concentration of absorbing substance in mole later inverse, L is the path length or thickness in the centimeter of cell containing the sample, epsilon proportionality constant known as molar absorptivity, sometimes referred to as molar extension coefficient or simply extension coefficient. The expression logarithm I naught pi is termed optical density or absorbance A. It is measure of absorption of the radiation by the sample. Therefore, Beard-Lambert law may also be expressed mathematically as A is equals to logarithm I naught pi I is equals to epsilon dot C dot L. Limitation of Beard's-Lambert law. Beard's-Lambert law is strictly obeyed when with dealing with the UV spectra of single species. However, if the sample contains different structural forms of the molecule in the equilibrium with each other, such as in the case of ketoenolautomers, the law is not obeyed. It is also not applicable if the solute sample and the solvent interact with each other to form complexes. Fourth, molar absorptivity, epsilon. It is a proportionality constant which relates the observed absorbance A at the particular wavelength lambda to the molar concentration of the absorbing substance and the length of the path in the centimeter. It may be expressed as epsilon is equals to logarithm I naught by I divided by CL, or absorbance divided by C dot L. Molar absorptivity is the measure of intensity of the absorption at a particular wavelength and has the dimensions of centimeter square mole inverse, but these units are seldom used. It is a characteristic property of compound and it is not affected by its concentration or the length of path of the light. Its value ranges from 0 to 10 to power 6. Value above 10 to power 4 constitute high intensity absorption, while value below 10 to power 4 are low intensity absorption. Percent transmission. Since I naught by I is the ratio of intensity of the incident light I naught to a transmitted light, the transmittance T of the sample will be naturally given by the reaction T is equals to I by I naught. It means percentage transmittance is equals to 100 into I by I naught. Mechanics of recording the UV spectrum. Presentation of the spectrum. Excellent UV spectrometers are now available which can conventionally record the spectra over the range 200 to 800 nanometer. 200 to 400 nanometer is known as near ultraviolet region, where 400 to 800 nanometer is visible region. Since oxygen of the atmosphere strongly absorbs light at about 200 nanometer and below, the use of wavelength shorter than 200 nanometer is not practicable unless special vacuum technique are employed. The ultraviolet spectra are always recorded on the wavelength scale in millimicrons or nanometers procedure. For recording the ultraviolet spectrum, the given compound is generally dissolved in some suitable solvent which does not itself absorb light in the region under examination. The commonly employed solvent are 95% ethanol, hexane, and water. The solution of the compound is placed in the suitable transparent container which does not absorb light in the region being studied. Generally, a quartz cell of 1 centimeter path length is used for this purpose. Glass cannot be used since it absorbs strongly in ultraviolet region. At the same time, some solvent is taken separately in another quartz cell which serves as reference cell. The sample solution and the solvent are then exposed to the ultraviolet and visible radiation in the spectrometer, in which the hydrogen discharge lamp is usually employed as a source of light in the ultraviolet region 200 to 400 nanometer, while a tungsten filament lamp is used for the visible region 400 to 800 nanometer of the radiation. The spectrometer operates by comparing the amount of light in the beam transmitted through the sample with the reference beam which passes through the reference cell. This compensates for any absorption of light by the cell and the solvent. In this way, the spectrometer measures the amount of light absorbed by the compound at each wavelength of the ultraviolet and visible region. This absorption gets recorded on the chart part as a plot of wavelength of the entire region on the horizontal axis versus the absorbance of the light at each wavelength. The spectrum observed contains a small number of broad peaks. Quite often, only one peak is seen. UV spectrometer. A simple simplified diagram of UV visible spectroscopemeter is shown in figure 4.2. It consists of the following part. First is the source of radiation, which emits all wavelength of UV radiation. The commonly used source of light in UV region is the hydrogen or deuterium discharge lamp, while a tungsten filament lamp is used for producing visible light. A monochromator, which separates the radiation into individual wavelengths. The single wavelength of radiation is split into two beams, one of which passes through the sample cell while the other passes through the reference cell. A detector which continuously measures the intensity of ratio of the beam transmitted through the sample and the solvent respectively. A recorder chart paper which automatically records the absorption of light at each wavelength has a graph of absorbance versus wavelength. Presentation of spectrum. The ultraviolet spectrum of 1 to 3 butadiene CH2 double bond CH single bond CH double bond CH2 in hexane is shown in figure 4.3. It may be seen that absorption of ultraviolet radiation by 1,3 butadiene begins at wavelength below 200 nanometer and continues up to about 260 nanometer. The absorption is maximum at 270 nanometer top of the peak. In reporting the UV spectrum for analytical process, the molar absorptivity epsilon, which indicates the intensity of absorption at the wavelength of maximum absorbance, is also quoted. Along with lambda max, for example, the molar absorptivity of 1,3-butadiene lambda max is equals to 217 is 20900. Therefore, the UV spectrum is reported as 1,3-butadiene lambda max is equals to 217 nanometer, epsilon is equals to 20900. Sometimes the ultraviolet absorption curve are also presented by plotting molar absorptivity against wavelength. For example, the ultraviolet spectrum of acetone in hexane plotted as epsilon versus wavelength is shown below in figure 4.3a. It may be seen that the maximum molar absorptivity epsilon is about 15 at lambda max is equal to 279 nanometer. Since the UV spectrum generally show broad peaks and valley, the actual spectrum are rarely used. The spectral information is given by listing the values of lambda max along with the molar absorptivity for each value of lambda max. Principle of UV spectroscopy. Absorption of visible and ultraviolet light produce change in the electronic states of molecule associated with the excitation of the electron from a lower to a higher energy level, but it must be noted that each electronic level in a molecule is associated with a number of vibrational sublevels with same energy, small energy separation, and each vibrational level in turn is associated with a number of rotational sublevel with still smaller energy separation. Therefore, in its transition to higher energy level, an electron can go from any of the sublevel corresponding to various vibrational and rotational state in the ground state to any of the sublevel in excited state. For example, in figure 4.4. Appearance of broadband and node sharp peaks in the spectrum. If the electronic excitation in a molecule had occurred without any accompanying change in vibrational and rotational sublevel, the spectrum would have consisted of a sharp line, as in the case of absorption spectra of atom, with each line representing a change in electronic state. But due to the mixing of vibration rotational change with electronic change in the molecule, there will be a large number of possible transitions requiring only slightly different energies. This will require the absorption of a large number of wavelengths which are very close to each other. As a result, the absorption spectrum contains a large number of lines which are too close together to be distinguished separately and are recorded in the form of broadband. In the spectrum obtained, as stated earlier, the spectrum is described in terms of the position of top of the hump lambda max and the molar absorptivity epsilon max. Electronic excitation. Electronic transition involve the promotion of an electron from one orbital to another orbital of higher energy. In a molecule, the electron promoted may be first a sigma electron, an electron present in the sigma molecule orbital, a pi electron in it means an electron present in a pi molecular orbital, or an electron it means an electron present in the non-bonding orbital is as illustrated with the help of electron pair in formaldehyde as shown in the right hand side. The higher energy orbitals are antibonding molecular orbitals which may be vacant in the ground state of the molecule. The antibonding orbital associated with the sigma bond is called the sigma star orbital, and that associated with the pi bond is called pi star orbital. Since the n electrons are not concerned in the bond formation, there are no antibonding orbital associated with them. The electronic transition taking place in the ultraviolet and visible region are of the following type: sigma to sigma star, n to sigma star, n to pi star, and pi to pi star. Figure 4.5 gives a general idea of the relative amount of energy required for various types of electronic excitation. A brief account of various types of electronic transition is as follows. First is sigma to sigma star transition. The transition in which a sigma bonding electron is excited to an anti-bonding sigma star orbitals are called sigma to sigma star transition. These transitions can be shown only by compounds such as saturated hydrocarbon in which all valence shell electrons are involved in the formation of sigma bond. The energy required for these transitions is very high, and consecutively they occur a very short wavelength. For example, in methane, the absorption of energy for such transition occur at only 1 to 5 nanometer. Since these wavelengths are lesser than 200 nanometer and fall in the vacuum UV region, the usual spectroscopic technique cannot be used in case of such transition. Second is N to sigma star transition. These are the electronic excitation from a non-bonding atomic orbital to an anti-bonding sigma star orbital. Compounds having a non-bonding electron on heteroatoms such as oxygen, nitrogen, sulfur, or halogen can show N to sigma star transition. These transitions are of lower energy and hence occur at lower wavelength than sigma to sigma star transition. For example, N to sigma star transition is in methyl chloride require absorption of energy at 174 nanometer. The required for these transitions decrease with the decrease in the electromagnetism of the heteroatom, and therefore the wavelength of absorption increases. For example, methyl chloride absorb at 174 nanometer while in methyl iodide absorption take place at 258 nanometer. Similarly, amines absorb at high wavelength at alcohol as nitrogen has lesser electronegativity than oxygen. This absorption can be attributed to the fact that greater the electronegativity of the heteroatom, more firmly the non-bonding electrons are held by it, and therefore more energy is required for N to sigma star transition. Hydrogen bonding of the compound with the solvent also shift the absorption to the shorter wavelength. But in general, N to sigma star transition are not of much importance. Third is N to pi star transition. These are the transition in which an electron in a non-bonding atomic orbital is promoted to an anti-bonding pi star orbital compound having double bond between heteroatom, example C double bond O, C double bond S, and nitrogen double bond O, shows these transition which appears as weak absorption band. These transitions require only small amount of energy and take place within the range of ordinary ultraviolet spectrometer. However, the intensity of absorption is generally very low. For example, the carbonyl group of saturated aldehyde or ketone exhibits an absorption of low intensity at about 285 nanometer. Fourth is pi to pi star transition. The transition in which an pi electron is excited to an antibonding pi star orbital are called pi to pi star transition. These have relatively higher energy requirement than n to pi star transition, and absorption generally take place outside the ordinary ultraviolet region for simple molecule containing isolated unsaturated centers, but the intensity of absorption is very high. For example, the pi to pi star transitions for a simple aldehyde or ketone produces an absorption band of high intensity at about 180 nanometer. For the simple alkene like ethylene, such a transition take place in still for far ultraviolet region about 175 nanometer. Effect of conjugation. Conjugation of double bond lower the energy required for the electronic transition. As a result, molecule containing conjugation systems such as C double bond C, single bond C double bond C, and carbon double bond carbon single bond carbon double bond oxygen absorb the radiation of longer wavelength than in case of non-conjugated system, and absorption band appear in the ordinary ultraviolet region. For instance, 1,3-butadiene shows lambda max 217 nanometer in contrast to ethylene, which shows lambda max 175 nanometer. To understand the effect of conjugation, On lambda max, let us start with ethylene, which is the simplest unconjugated alkenes. The double bond in ethylene consists of the sigma bond formed by the combination of sp2 hybrid orbitals of the two carbon atom and a pi bond formed by the combination of the unhybrid 2p orbital. Due to the large difference in the energy of the pi bonding and pi antibonding molecule orbitals, pi to pi star transition take place with the absorption of radiation below 200 nanometer 175 nanometer of ethylene. Therefore, these transitions occur only in the far ultraviolet region. In a conjugated system such as 1,3-butadiene, there are two ethylene units in the conjugation with each other. Due to the conjugation, the pi bonding orbitals of the two ethylene units interact with each other to form the two new bonding orbital pi and pi star of the different energy. Similarly, there is a formation of two pi orbital pi 3 star and pi 4 star of different energy from two ethylene unit. The energy difference between highest occupied pi molecular orbital and the lowest unoccupied molecular orbital for 1,3-butadiene is less than for ethylene, as the HOMO to LUMO energy gap between becomes smaller. The position of energy absorption moves to longer wavelength, which falls within the ordinary ultraviolet region. With the increase in the number of double bond in conjugation, the energy difference between HOMO and LUMO further decreases, so the absorption moves to still longer wavelength. The spectrum of 1357 octatetrane in hexane exhibits lambda max 290 nanometer. If there are enough double bond in conjugation, absorption still will ultimately moves into a visible region and the compound will become colored. For example, beta carotene, a naturally occurring yellow pigment containing 11 double bond in conjugation, owes its color to the absorption in visible part of the light. Another effect of conjugation is that with the increase of conjugation, the number of possible UV transition increases and the spectrum become more complex. To sum up the above discussion on electronic transition, it may be stated that the organic chemist is primarily interested in two types of transition, particularly in conjugated system. These are N to pi star, for example, carbon double bond oxygen to carbon double bond oxygen, and pi to pi star, for example, carbon single bond oxygen give rise to carbon single bond oxygen. It may be noted that transition to antibonding pi star orbital are associated only with unsaturated center in the molecule. Transition probability. It is interesting to note that it is not necessary that exposure of the compound to ultraviolet or visible light must be always led to an electronic transition. On the other hand, the probability of the particular electronic transition depend upon the value of molar absorptivity, epsilon max, and the certain other factor. Accordingly, transition have been divided into two categories. First is allowed transition and second is forbidden transition. Allowed transition. These are the transition in which have epsilon maximum 10 to power 4 or more and the probability of their occurrence is very high. These are generally due to the pi pi star transition. For example, pi to pi star transition in 1,3-butadiene which show absorption at 270 nanometer and has epsilon max 20900 represent an allowed transition. The pi and pi star orbital involved in these transitions lie in the same plane and can undergo overlapping to a large extent in the excited state. Therefore, pi to pi star transition are highly probable. Forbidden transition. These are the transition for which epsilon max is generally less than 10 to power 4. These are usually related to N to pi star transition. For example, N to pi star transition of the saturated aldehyde or ketone showing weak absorption near 290 nanometer and have epsilon max less than 100 is a forbidden transition. It should be clearly understood that the forbidden transition does not mean that such a transition cannot take place at all. It just tells us about the probability of the transition is very low. To clarify this statement, let us consider the N to pi star transition. The orbital containing the non-bonding electron present on the heteroatom lie in the plane perpendicular to the plane of pi star molecular orbital. The region in space belonging to these orbitals can overlap only to very small extents. As a result, the probability of excitation of an electron to pi star orbital is very low. Concept of chromophore and auxochromes. Chromophore. The term chromophore was originally used to denote a functional group or some other structural feature, the presence of which impart a color to the compound. For example, nitro group of chromophore, since its presence in the compound, impart yellow color to the compound. But these days, the term chromophore is used in the much broader sense. It is now defined as any group which exhibits absorption of electromagnetic radiation in the visible or ultraviolet region. It may or may not impart any color to the compound. Table 4.1 lists some simple chromophore group along with their lambda max, epsilon max, and the type of transition involved. It may be seen that chromophore are of two types. First, chromophores such as carbon double bond carbon and carbon triple bond carbon, which contain pi electron and undergo pi to pi star transition. Second is chromophore such as carbon double bond oxygen, nitrogen double bond nitrogen, and NO2, in which contain both an pi and an electron. They can undergo pi to pi star as well as n to pi star transition. Two compounds having the same chromophoric group generally exhibits absorption at nearly the same wavelength and have nearly the same molar absorptivity epsilon max. Therefore, it should be possible to identify the presence of a particular functional group in an unknown compound by the comparison of its UV spectrum with the data of already known compound, but the position of absorption maximum and the intensity of absorption can be modified by the number of fractions. Oxochrome. An oxochrome is a group which itself does not act as a chromophore but whether attached to the chromophore, it shifts the absorption maximum towards longer wavelength along with an increase in the intensity of the absorption. Some commonly known oxochromic group are OH, NH2OR, NHR, and NR2. All oxochromes contain one or more non-bonding pair of electrons. When an oxochrome is attached to a chromophore, it leads to the conjugation or help in extending conjugation by sharing of its non-bonding pair of electrons as shown below. Due to the conjugation, there is decrease in an energy difference between the ground state and excited state of the group. As a result, the absorption shifts to the longer wavelength. At the same time, there is an increase in the intensity of absorption. For example, when the oxochrome NH2 group is attached to the benzene, it increases lambda max as well as epsilon as given below. Lambda max is equals to 255 nanometer increases to 280 nanometer, whereas epsilon 203 nanometer increases to epsilon max 1430. NH2 act as oxochrome by extended the conjugation in benzene by participation of non-bonding pair of electron in the conjugation. Similarly, the ethoxy group act as an oxochrome as shown below. Change in the position and intensity of the absorption. For isolated chromophore groups such as carbon double bond carbon and carbon triple bond carbon, absorption occur in far UV region which cannot be easily studied, but the position of absorption maximum and the intensity of absorption can be modified in different ways by some structural changes or the change of solvent. These changes can produce four kinds of effect. First is bathochromic shift or red shift. Second is hypsochromic shift or blue shift. Third is hyperchromic shift. Fourth is hypochromic effect. These effects are discussed below. First is bathochromic shift or red shift. It involves the shift of absorption maximum towards the longer wavelength. It can be brought about by three different methods as given below. First, by attachment of an oxochrome to the chromophore. When an oxochrome such as OH or NH2 is attached to the chromophore, it leads to the conjugation or help in extended conjugation. As a result, absorption shift to the longer wavelength, as already explained in section 4.92. For example, when the Ancochrome NH2 group is attached to the benzene ring, it shifts the absorption band from 255 nanometer to 80 nanometer. By conjugation of two or more chromophoric group, bathochromic shift is also produced if two or more chromophores are present in conjugation in a molecule. For example, as already stated, ethylene shows pi to pi star transition at 170 nanometer, while 1,3-butadiene shows lambda max at 217 nanometer. Third is by using solvent of low polarity. It is also possible to achieve bathochromic shift by using solvent of lower polarity. For example, use of solvent of lower polarity produces a red shift in the N to pi star absorption of carbonyl compound. Acetone shows lambda max at 264 nanometer in H2, but it shifts to 279 nanometer when hexane is used as solvent. Hypsochromic shift or blue shift. It involves a shift of absorption maximum toward shorter wavelength. This may be brought about as follows. First is by removal of conjugation in the system. For example, protonation of aniline causes a blue shift from 280 nanometer to 203 nanometer. This is because an alinium ion thus formed has no lone pair of electron nitrogen which can conjugate with the benzene ring. By using solvent of high polarity, use of solvent of high polarity can also bring about hypsochromic shift. For example, use of solvent of high polarity causes a blue shift in the N to pi star absorption of the acetone. Hyperchromic shift. This effect involves an increase in the intensity of absorption. It is usually brought about by introduction of an oxochrome. For example, introduction of methyl group in the position of 2 of pyridine increases lambda max from 2750 to 35604 pi to pi star transition. Hypochromic effect. It involves a decrease in the intensity of absorption. It is brought about by the group which distort the geometry of the molecule. For example, when a 2-methyl group is introduced in the position of 2 of biphenyl, hypochromic shift effect take place due to the distortion caused by the methyl group. As a result, lambda max decreases from 19,000 to 10,250. It may be noted that bathochromic shift is generally accompanied by hyperchromic effect, while hypsochromic shift is accompanied by hypochromic effect. The various kind of absorption and intensity shift have been summed up in Figure 4.7. Solvent effect and choice of solvent. First is solvent effect. The solvent used for dissolving a compound under examination has a profound effect on the UV spectrum of the conjugated as given below. First is the effect on fine structure. As a result of interaction of solute with the solvent molecule, the fine structure of the absorption bands is blurred out and a smooth curves is obtained. The smoothing out of the spectrum deprives us of the much useful information about complex molecules. The smoothing out effect in more is more polar in the solvent than in the non-polar solvent. The fine structure of UV spectrum is best observed in the vapor phase. Second is the effect on the position and intensity of absorption maximum. Changing the polarity of the solvent may also lead to change in the position and intensity of the absorption maximum. Effect on non-polar compound. In general, change in the polarity of the solvent do not cause any significant shift in the spectra of non-polar compounds such as dienes and conjugated hydrocarbon. For example, the absorption maximum for non-polar compound is practically the same in alcohol as well as in hexane. Effect on polar compound. In case of the polar compounds such as alpha, beta, and saturated carbonyl compound, the absorption maximum generally gets shift with the change in the polarity of the solvent. It has been observed that such shift are of two types. First is shift in N to pi star transition. Increase in the polarity of the solvent shift N to pi star transition to shorter wavelength. For example, absorption maximum of acetone is at 279 nanometer in hexane, at 270 nanometer in ethanol, and 264 nanometer in water. The shift towards a shorter wavelength is mainly due to the greater stabilization of ground state than the excited state through dipole-dipole interaction, formation of hydrogen bond, or the solvation with the polar solvent. As a result, the difference in the energy between the ground state and the excited state increases and the absorption shift towards shorter wavelength. Let us, for example, consider the blue shift of the N to pi star carbonyl absorption. The carbonyl group is more polar in ground state than in excited state. Therefore, the extent of the hydrogen bonding between the ground state and the polar solvent like water and alcohol is much more than between the excited state and the solvent. In other words, ground state is stabilized to a greater extent and undergo greater lowering of the energy than the excited state. Consecutively, the energy difference between the two states increases and the absorption shift takes place towards the shorter wavelength. Second is shift in pi to pi star transition. Increase in the polarity of the solvent shift pi to pi star transition to the longer wavelength. Red shift, for example, it has been observed that as compared to the solution in hexane solution in ethanol generally shows a red shift of about 10 to 20 nanometer. The shift of pi to pi star absorption towards longer wavelength is largely due to the greater stabilization of excited state relative to ground state through dipole-dipole interaction or solvation. As a result, the energy difference between the ground state and the excited state decreases and the absorption shift towards longer wavelength. For example, the molecule of ethylene is more polar in the excited state than the ground state due to the greater polarity of pi star orbital compared to the pi orbital. As a result, the pi star molecular orbital will be relatively more stabilized by dipole-dipole interaction with the polar solvent as compared to the stabilization of ground state. Therefore, lesser energy will be required for such a transition and the absorption will shift toward longer wavelength. Third is shift in N to sigma star transition. N to sigma star transition are very sensitive to hydrogen bonding. For example, alcohol and amines form hydrogen bonding with the solvent molecule due to the presence of non-bonding electron on the heteroatom. As a result, more energy is required for N to pi star transition in polar solvent and shift towards lower wavelength take place. To sum up, if a group is more polar in the ground state than in the excited state, increasing the polarity of solvent shift the absorption to shorter wavelength, and if the group is more polar in the excited state than the in ground state, increasing the polarity of the solvent shift the absorption to the longer wavelength. Choice of solvent. A suitable solvent for ultraviolet spectroscopy should meet the following requirement. First, it should be transparent in the wavelength region under examination. It should not itself absorb radiation in the region being examined. Second is it should be less polar so that maximum interaction with the solute molecule and has no effect on the fine structure of absorption band and the position of the absorption band. The most commonly employed solvent is 95% ethanol. It is cheap, has good dissolving power, and does not absorb radiation above 210 nanometer. In other words, it is transparent above 210 nanometer. Commercially, ethanol should not be used as it contains some benzene which undergo absorption in the UV range at about 280. Some other solvent which are transparent about 210 nanometer and N-hexane, cyclohexane, methanol, water and ether hexane and other hydrocarbon are sometimes preferred to polar solvent because they have minimum interaction with the solute molecule. Benzene, chloroform and carbon tetrachloride cannot be used because they absorb in the range of about 240 to 280 nanometer. Some characteristics absorption band. Table 4.2 lists the wavelength of maximum absorption and corresponding molar absorptivity of or extinction coefficient for some typical ultraviolet band of simple molecule containing different groups. Woodward-Fisher rule for calculating absorption maxima. By studying the UV absorption spectra of large number of compound, Woodward deduced certain rule for correlating lambda max with molecular structure. Since then, these rules have been modified by Scott and Fisher as a result of more experimental data. The modified rule known as Woodward-Fisher rule enables us to calculate the position of lambda max for a given structure by relating the position of lambda max with the position and degree of substitution of chromophore. The calculated value are generally within 2 or 3 nanometer of experimental value. We will now consider these rules briefly for different classes of compound. Woodward-Fisher rule for calculating lambda max in conjugated dienes, trienes, and polyenes. Before we consider the rules for dienes, trienes, or etc., it should be useful to explain some term involving in the discussing the rules. First is homoannular diene. It is a cyclic diene which contain conjugated double bond in the same ring. For example, heteroannular dienes. It is a cyclic diene in which double bond in conjugation are present in different ring. Endocyclic double bond. It is a double bond present in the ring as shown below in structure A. Exocyclic double bond. It is a double bond in which one of the doubly bonded atom is a part of the ring system, as shown above in figure 2. Woodward-Fisher rule for conjugated dienes, trienes, polyenes, etc. According to this rule, each type of diene or triene system has a certain fixed value at which absorption takes place. These constitute the basic value or the parent value. The contribution made by various alkyl substituent or ring reduced residue, double bond, extended conjugation, and polar groups such as chlorine, bromine, and OR are added to the basic value to get lambda max for a particular compound. The parent value and contribution of different substituent groups are given in table 4.3. For example, parent value first is acyclic conjugated dienes is 217 nanometer, homoannular conjugated diene 253 nanometer, heteroannular conjugated diene 214 nanometer. If increments are added for each alkyl substituent or ring residue 5 nanometer, exocyclic double bond 5 nanometer, each double bond extended conjugation 30 nanometer, oxochrome OR 6 nanometer, SR 30 nanometer, chlorobromo 5 nanometer, NR2 60 nanometer, and OCOCH3 0 nanometer. To illustrate the above rule, a few examples are given ahead. Woodward-Fisher rule for alpha-beta unsaturated carbonyl compound. Woodward-Fisher rule for calculating lambda max for alpha-beta unsaturated carbonyl compound modified by Scott may be summed as given below in the table 4.4. Parents value first is alpha-beta unsaturated acyclic or 6-membered ring ketone is 215 nanometer. Alpha-beta unsaturated 5-membered ring ketone is 202 nanometer. Alpha beta unsaturated aldehyde is 207 nanometer. Increments are each alkyl substituent or ring residue at alpha position 10 nanometer, beta position 12 nanometer, and gamma and higher position 18 nanometer. Exocyclic double bond 5 nanometer, double bond exocyclic to two rings simultaneously 10 nanometer, double bond extended conjugation 30 nanometer, homoannular conjugated lines 8 13 9 nanometer. Oxochromes OH at alpha position 35, beta 30, and gamma 50. OR group if present at alpha 35, beta 30, and gamma 17. OCOCH3 at alpha position 6, beta 6, and gamma 6. Chlorine group alpha position 15, beta position 12. Bromine group alpha position 25 and beta 30, and NHR2 beta position 95. In these compounds, the actual spectra obtained are affected considerably by the nature of the solvent employed. Therefore, a solvent correction is applied to the calculated value to obtain the value for that particular solvent. However, we are not discussing the solvent correction at this stage. A few examples are given below for the sake of illustration. Interpretation of UV spectrum. Application of UV spectroscopy. The interpretation of UV spectrum of unknown compound can be very useful in deriving structural information about the compound. The main application of UV spectroscopy are as follows. First is detection of conjugation. UV spectrum help to show whether a given compound contains certain group in conjugation with each other or not. The conjugation may be between two or more carbon-carbon double bonds, between carbon-carbon and carbon-oxygen double bonds, or between double bonds and a aromatic ring. UV spectrum can also reveal the presence of an aromatic ring itself and the number and location of substituent attached to the carbon of the conjugated system. For example, let us compare the UV spectrum of 4-methyl pent 3 in 2-on and 4-methyl pent 4 in 2-on. Since 4-methylpent 2 in 3 in 2-on has the carbon-carbon double bond and the carbonyl group in conjugation with each other, both pi star and the n sigma pi star absorption band in it will be longer wavelength than in 4-methylpent 4 in second, in which there is no conjugation. Thus, UV spectrum enable us to determine whether a compound contain a conjugated system or not. Extent of conjugation. UV spectroscopy is also employed to estimate the extent of conjugation in polyenes. With the increase in number of double bond, the absorption shift to longer wavelength. For a compound having 8 or more double bond, the absorption may shift to even visible region of light. Thus, by determination of lambda max of given polyenes, it may be possible to know the number of double bond in the conjugation. Determination of configuration of the geometrical isomerism. In case of geometrically isomer compound, the trans isomer exhibit lambda max at slightly longer wavelength and large absorptivity than the cis forms. For example, of the two still beans, the trans isomer shows lambda max at 294 nanometer, while in cis isomer lambda max is 278 nanometer. The above observation can be justified in terms of steric hindrance. In the trans isomer, the bulkyl group lie on either side of the double bond and there is no steric hindrance. As a result, the ethylenic double bond and the pi double bond of benzene ring lie in the same plane and the pi orbital overlap of the conjugated system is quite effective. Therefore, the trans isomer absorb at longer wavelength. In the cis isomer, the bulkyl group lie on the same side of the double bond, giving rise to steric hindrance. Therefore, the ethylenic double bond and the pi bond of benzene are forced to the non-plane to be non-planar. Due to this distortion, the pi orbital overlap is not so effective. The decrease in pi orbital overlap led to decrease in conjugation. Hence, the cis isomer absorbs at shorter wavelength. Fourth is detection of functional group. UV spectrum can be used for the detection of certain functional group and the other structural feature of the absorption take place above 200 nanometer. Even the absence of any absorption above 200 nanometer is of some utility as it shows the absence of conjugation carbonyl group and the benzene ring in the compound. Determination of strength of the hydrogen bonding. If a compound form hydrogen bond with a protic solvent such as water and alcohol, it is possible to find the strength of hydrogen bonding by comparing the lambda max in the protic solvent with lambda max in a non-polar solvent. For example, carbonyl compound form hydrogen bond between water and carbonyl oxygen. As a result, the energy of an electron of carbonyl oxygen in the ground state decreased by the amount equal to the strength of the hydrogen bond. Consequently, the n pi star transition of carbonyl compound require more energy and therefore it is shift to lower wavelength. For example, N5 star transition of acetone in hexane take place at 279 nanometer, but in water it occurs at 264 nanometer. From the above high hypsochromic shift at 15 nanometer, the strength of hydrogen bond between water and acetone can be calculated. Study of ketoenol tautomerism. In case of compound which exhibits ketoenol tautomerism, UV spectrum show characteristic absorption band of both the keto and enol forms. For example, lithyl acetoacetate, which exists as an equilibrium mixture of keto and enol tautomers, shows two absorption band for the keto and enol form respectively. The keto form has lambda max to 75 nanometer with very low intensity, while the enol forms has lambda max to 44 nanometer with very high intensity. Seventh is quantitative analysis. UV spectroscopy provides a very sensitive method of quantitative analysis. It is based upon Baird-Lambert law, which relates the absorbance of the substance with its concentration, path length, and molar absorptivity, that is, A is equals to epsilon C L. For example, we can find the concentration of vitamin A in the sample by determining the absorbance of the given sample. Pure vitamin A has lambda max 325 nanometer. If the given sample, when taken in the cell with a path length of 1 centimeter, shows an absorbance of 0.75 at 325 nanometers concentration can be calculated as follows. Purification control. UV spectroscopy is also used for purification control in dye stuff and pharmaceutical industries. Thank you.